Okay, our topic is force systems resultants. So we have already we learned that in physics how to calculate the moment of a force. Okay, so certainly when you want to calculate the moment of a force, let's say that the force is located at a distance of d and the moment is mo. So I want to calculate the moment of a force F with respect to point O. Then what I do is simple. I multiply the force with the distance, the perpendicular distance, or perpendicular distance of the force to that point. So this is how I calculate the moment of a force. Okay, but what if we have more than one force? So we basically calculate the force of moment of each force, then we sum up and arrive at the moment around that point. This is mostly the case for planar problems. What if we have a three-dimensional problem? So how can we calculate the moment in such a case? First thing that we have to know is the moment is a vectoral quantity. Okay, now there is something we have to define in this case, which we haven't seen before in any of the previous courses, either in physics or other ones. Vector product. Now consider that we have two vectors, A and B. Now we can define an operator which we call vector product, and generally we show it with the cross. And A vector product B gives us a vector. Remember that the scalar product of two vectors gives us a scalar quantity, but now here the vector product of two vectors gives us a vector. And indeed, this vector is always perpendicular to the two other vectors, A and B. So this angle is 90 degrees and this is 90 degrees as well. Okay, now remember that we have defined the unit vectors. Now here the point is, okay, A is a vector and B is a vector. That's okay, right? And how can we define the direction of the third vector? Okay, they are perpendicular. It's perpendicular, but we need to define how we have to define its direction. Now in this case we use the right hand rule. Now just imagine that I have two vectors, okay? As you see, so these two pens are my vectors. Moment, maybe it is better like this. Yeah. So they have arbitrary direction in space. Now what I do is I put my hand on one of the vectors and curl my finger towards the other, and as you see my thumb shows the well, okay, sorry. This is a touch pen, so you see the red lines. So it's like this. Let me find another pen then. That's okay, so that's better. Now it's like this. You have two vectors, and I put my elbow on one of it and curl my finger towards the other, and in this case my thumb shows me the direction of the third vector. You see? So I use the right hand rule. Basically this is what we call right hand rule. In fact, what you do is like this. You put your elbow on the vector A and then curl your fingers towards the second vector, and certainly your result is in the direction of your thumb. Okay, so this is how I find the direction of the resultant vector, the result of the vector product of two vectors. In fact, I have been using unit vectors, right? So we define a vector in a Cartesian form generally. So we have the unit vectors in x, y, and z coordinates, and respectively we define I, j, and k in each direction. So I for the x-axis, and j for the y-axis, and k for the z-axis. Now the point is this. Certainly I know that I, j, and k are perpendicular. So I vector product j gives me the vector k. This is unit vector k. Okay. Now here is another thing. J vector product I gives me minus k because of the right hand rule. Simple. K vector product I. So I directed my fingers from, I put my elbow on the z-axis and curl my fingers towards the x-axis, and as a result my thumb will show me the y-axis. So it is j vector. Again, I vector product k. So I put my elbow on the I vector on the x-axis and then curl my fingers towards the z-axis, and as a result my thumb will show me the negative y-axis. As a result, I vector product k will give me negative j. Be careful, I vector product I is 0 because you cannot curl your fingers. Vector product of the same vector, so basically any two vector product of any two vectors which shows the same direction will be 0 automatically. As you see here, it is j vector product j is equal to 0 and j vector product k is equal to I, because here, for example, you put your elbow on the y-axis and then you curl your fingers towards the z-axis. As a result, your thumb will show the positive x-axis, and therefore the multiplication of unit vector j with unit vector k will give you unit vector I. And it goes like this for the other axis. So okay, so basically this means that there are some properties that we have to properties of vector product. So remember that changing the places of vectors will change the result, because A vector product B is not equal to B vector product A, and certainly A vector product B is equal to negative of B vector product A. It has distributive property, so just assume that you sum up two vectors and you multiply it with A. Okay, so as a result, A vector, this is equal to A vector product B plus A vector product C. Okay, now let's calculate the A vector product B first. So how we can do it? First, write the any vector A. It has A has the x component AX, y component AY, and z component AZ. Of course, B vector B has the x component BX, y component BY, and z component BZ. Now, how you do it? You multiply each term of the first vector with the components of the second vector, and then you sum up them. Now let's look. AX I multiplied by BXI. I know that I vector product I is equal to 0. So this multiplication will give you 0. Okay. Now I will multiply it with the second term. Okay. AX I multiplied by BYJ. First, I multiply the coefficients. So AX multiplied by BY. Now I multiplied by J. Now in this case, what I do is very simple. I put my elbow on the x-axis and curl my fingers towards the y-axis, and my thumb will show me the positive z direction as a result. So this means that I vector I multiplied by j will give you k vector, and the coefficient is ax multiplied by by. So it's here. Okay, let's continue further. Now I will multiply these terms. So AXI multiplied by BZ K vector. Okay, now first I multiply the coefficients. Certainly it is AX multiplied by BZ. Now I will multiply I. So it's I vector product K. Therefore, what I do is, again, I put my elbow on the x-axis. Now my fingers will be directed towards the z-axis. If you think that the z-axis is towards the upwards. Now you see my thumb shows the negative y direction. So as a result, it is AX multiplied by BZ minus J vector. So it is minus AX BZ J. So it is this term. Certainly you do the same thing for the second term of the first vector. So you multiply it with this one. Let's do it like this. First clean the screen. Yes. For the second term you do the same thing. So first you take this term and then you multiply it with this one, then you multiply it with the second one, then you multiply it with the third one, and then you obtain the results vectors for each multiplication, for each vector product. Then you do the same thing for the third one. So you multiply this term with this one, and then you multiply this term with this one. So they are all vector of multiplication or vector product, and then you multiply this term with this one, and as a result you obtain this expression for the vector product. So this is the result of the vector product of A vector product B. Okay, so this is one approach. So you can do it algebraically, but in fact there is another approach that you can use. What you do is you can write the vectors in matrix form. First, in the first row you write the unit vectors I, j, and k. Then you write the components of the vector, first vector, in each direction. So ax, ay, and az. Then in the last row or third row you write the components or coefficients in each direction, or components of the vector in each direction, bx, by, and bz, and then you have to calculate the determinant of this matrix. So how we calculate the determinant of this matrix? You can choose any row. If you choose the first row, first you give the plus, minus, and plus, and then you exclude the first column and first row, right? Yes. Then you calculate the determinant of this 2 by 2 submatrix. So this is ay multiplied by bz minus by multiplied by az multiplied by I. So this will be the I component or x component of the vector. Then what you do is, next, now you continue to sum up, but first again you exclude the first row and second column. Now again you have a 2 by 2 matrix. In this case submatrix. This submatrix has a determinant of ax multiplied by bz minus bx multiplied by az. But in this case you multiply it with the j and you put a minus sign in front of it, and you do it for the third column as well. So this is how we calculate the determinant. At the end you arrive at this expression again. Okay, now this is a vector product. Now we have seen how to calculate a moment for for planar problems, but how can we calculate a moment for multidimensional or three-dimensional problems? So what is the definition of the moment? Now just consider a force in space, a single force, a vector. Now this force acts at a point. Certainly this point has a position vector. Let's say that we have a reference point, any reference point, and indeed the position vector of this force is r, and the force vector itself is f. Then the vector product of the position vector with the force will give us the moment vector Be careful, moment is a vector. So moment vector with respect to that point. This is how we calculate the moment of a force with respect to a point. Okay, then we can write the moment vector with respect to a point as a determinant of this matrix. So here again the first row is the unit vectors in each direction, x direction, y direction and z direction. Then we have the position vectors in x direction, in y direction and in z direction, certainly the components of the position vector in the second row. And in the third row we have the components of the force vector, f of x, fx, fy and fz. Okay, so now we have calculated a force, moment of a force. Now the point is, what if we have more than one force? This is generally the case in many of our designs, right? So just think that in many structures you have the column, you have the load on it, coming on it, you have perpendicular forces and so on. So therefore you have more than one force in general. In this case what you do is you calculate the force moment generated by each force with respect to that specific point, or with respect to a specific point, and then you sum them up. So this is how you calculate the moment if there exists more than one force. Now let's look at another case. In some cases we need to calculate the moment of a force along a certain axis, in the direction of a certain axis. In for example the shafts, right? So you fix them, there are bearings and shaft is rotating, and I want to calculate the moment in the direction of the shaft. So that moment will generate the turning motion, rotating motion. So what I do is, first I calculate the moment. Then, so this is my force and this is my position vector of my force with respect to a point on the axis. Let's say that my axis is from O to A, OA. First I calculate the moment with respect to O. Then I calculate the unit vector along the axis, UOA. We have seen how to calculate the unit vector, right? Indeed, what I do is then I do a scalar multiplication of the unit vector with the moment vector, because moment vector can be in any direction. For example, like this. Generally I show the moment vector with double arrow. So when you, in case of a force we put single arrow, but generally we define the we show the moment with double arrow. Then we multiply this moment vector with the unit vector. So basically I take the projection of this moment vector onto the unit vector UOA. So this is how I calculate the moment of a force according to an axis, or on an axis. That's better maybe. Okay, so of course we may have some force couples in some problems. We will see it in detail. For example, Just think that you want to open a jar. So what you do is simple. So you turn it like this, right? I apply a force around it, and if I touch it like this, you see one of my fingers will try to turn this object in the clockwise direction, maybe in this direction, and the other one will try to rotate it in the other direction. So the force that they apply are in has opposite directions, but they may have the same magnitude. This is what we call force couple. In this case, how can we calculate the moment generated by these forces? Let's say that one of the forces are located at point A, acting at point A, and the other force is acting at point B. They have opposite directions. So one has F and but the other is minus F because they have opposite direction, but they have the same magnitude. Now what I do is very simple. I draw a vector from one to the other. So basically it is the shortest distance, we can say. Now let me draw the position vectors of point A and point B, and R is always perpendicular. In general. Now I want to calculate the moment generated by this. So I have a force couple. I have the relative position vector of either forces. First, remember that how I calculate the moment generated by a single force. It is the position vector multiplied by F, right? And the other one is RB. RB is equal to, so this is where the force is acting. So this is where the first force is acting, and the other one is the position vector where the other force is acting, RA, and the other one is RB. Now certainly the second vector is minus F. So RA multiplied by F plus RB vector, sorry, RA multiplied RA vector product F. Sorry for the confusion. RB vector product minus F. As a result, this minus will come out from here, and indeed I can write the F and take outside this subtraction operator. Now I will be left with RA minus RB, and certainly RA minus RB is the relative position of A with respect to B, which I define as R, and I will arrive at this formulation. So as a result, when I have a force couple, it is R vector product F. R is the relative position of one vector to the other.